Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams. Still on the beautiful subject chemistry, we'll be looking at a special theme tagged electrochemistry. Now, talking electrochemistry guarantees at least 5 to 6 to 7 questions answered correctly in your UTME exam. That is, if you take time to understand it, it guarantees you at least 5, 6, 7 questions that you will be able to answer correctly in your exams, and that should be roughly 15 marks. So, talking about electrochemistry, it is a branch of chemistry that deals with the relationship between electricity and chemical reactions. That is, in one way, we are looking at how we can use direct current or electricity to cause chemical decomposition or to split or chemical compounds in a process called electrolysis. That's, you're using electricity to bring about a chemical change. And as well, we'll be looking at a quantitative approach to it, talking about Faraday's laws of electrolysis. Also, in another way, we will be looking at how we can generate electricity from chemicals, talking about electrochemical cells or galvanic, or what we can as well call voltaic cells, and we'll be applying electrochemical cell understanding to batteries and, of course, corrosion, more specifically rusting of iron. So when you look at electrochemistry, you're basically looking at the relationship or the chemistry between electricity and chemical reactions. In one way, we want to use electric current to bring about the chemical decomposition of chemical compounds, that is talking electrolysis. In another way, we want to use chemicals to generate electricity, to generate flow of electron, talking electrochemical cells. But before we can understand electrochemical cells and electrolytic cells, we need a very good knowledge of redox reactions, talking oxidation and reduction reactions, to which we are now going to direct our attentions. But at the end of this theme, electrochemistry, we should be guaranteed at least another 15 marks as far as UTME chemistry is concerned. Now, moving into oxidation reduction reactions. When we talk oxidation reduction reactions, they are opposite reactions. Okay, moving on into oxidation reduction reactions proper. When we talk oxidation reduction reaction, abbreviated as redox reaction, reduction, oxidation. Oxidation reduction reactions are opposite reactions. When oxidation is performing a process, reduction is going to perform the exact opposite of that process. Yet, they complement each other. That is, in a given equation, once you have an oxidation reaction, then you definitely will have the opposite, talking about reduction reaction present. You cannot say in an equation you have only oxidation. It's not possible. Once an oxidation reaction is present in an equation, then you're definitely going to have reduction process in there. So we say oxidation reduction reactions are opposite reactions, yet complementary reactions. Every oxidation reaction is accompanied by a reduction reaction, and every reduction reaction is accompanied by an oxidation reaction. Talking about redox reaction, it is the interaction between oxidizing agent and reducing agent. More specifically, when you talk about oxidizing agents here, oxidizing agents will usually undergo reduction, and reducing agents will undergo oxidation, telling you that oxidation reduction reactions are opposite processes, but the two reactions complement each other. And when we are talking about understanding and defining oxidation reduction reactions very well. We define them in terms, in various terms. The first one we'll be looking at is we'll be looking at oxidation reduction reactions in terms of oxygen. We'll be looking at oxidation reduction reaction in terms of hydrogen. We'll be looking at the process in terms of electron transfer, and we will try to understand this using the oxidation number concepts. And I think after that we'll also be looking at the various rules for assigning oxidation number. We'll be looking at how we balance redox reactions using ion electron method. We'll also be looking at half equations. Yes, we'll be looking at half equations. We'll be looking at telling if a reaction is redox or not redox. We'll be looking at how we test for oxidizing agent and reducing agent. But most important thing is this. From here to here, once we can get this, much emphasis on in terms of electron and using the oxidation number concept, then redox reaction is going to be, a smooth sailing. Looking at redox in terms of oxygen, you need to understand that oxidation, I represent that this way. Oxidation is the addition of oxygen to a substance, while reduction is the removal. That's why I said minus oxygen from a substance. Simply, oxidation is plus oxygen, while reduction is minus oxygen from a substance. And what we undergo oxidation is the reducing agent, whereas what will undergo reduction is the oxidizing agent. Let's take this equation. Let's say, okay, we're looking at copper oxide reacting with zinc. In this reaction, zinc is going to displace copper, so that you have zinc oxide plus copper. When you look at this, the fact that oxygen has been removed from copper here, removal of oxygen from a substance is reduction, and what will undergo reduction here is our oxidizing agent tagged OA. Now looking at zinc, zinc had become zinc oxide. This here is oxidation, and in this case our zinc oxide is going to be the reducing agent. So when you talk in terms of oxygen, oxidation is the addition of oxygen to a substance, reduction is the removal of oxygen from a substance. Reducing agents will usually undergo oxidation, while oxidizing agents will usually undergo reduction. Let's take another example. Let's look at the case of okay, let's say steam, or let's say water plus carbon dioxide. Okay, in this case we're going to have carbon dioxide plus hydrogen gas. When I look at this, the fact that oxygen has been removed from this hydrogen tells me this is a reduction process, and what we undergo reduction is my oxidizing agent. And the fact that oxygen has been added to carbon monoxide to form carbon dioxide This process is what? Oxidation. And what we undergo oxidation here is my reducing agent. So looking at redox in terms of hydrogen, oxidation is the removal of hydrogen from a substance, while reduction is the addition of hydrogen to a substance. And what we undergo oxidation, don't forget, is your reducing agent, while what will undergo reduction is your oxidizing agent. Let's look at the reaction that just explains this better. Let's say we have sodium hydride plus potassium. Sodium hydride plus potassium. In this reaction, this is what we're going to have. Potassium is going to displace sodium, so that you have potassium hydride plus sodium. In this case, you look at sodium hydride becoming sodium. This is minus hydrogen. Hydrogen has been removed from the sodium here. So when you look at this process, this is oxidation, as oxidation is the removal of hydrogen. Oxidation is minus hydrogen from a substance. But when you look at potassium here, potassium had become potassium hydride. So in this case, this is my reduction process. And since the process, the two processes, they are opposites but complementary, reducing agent here is the one that will undergo oxidation. And my oxidizing agent, talking about potassium, this is my oxidizing agent here. My potassium will be the one to undergo reduction. So let's use another equation, another reaction to, Butter's oxidation reduction reaction in terms of hydrogen. Let's look at the conversion of ethanol to ethanol. Ethanol is C2H5OH. This is ethanol. Okay. I want to in converting this to ethanol, CH3CHO. More specifically, when you look at organic chemistry, H, and then so this is ethanol. It belongs to the aldehydes or alkanals. Now let's have a solution of ethanol laced with acidified potassium heptaozodichromate 6 K2Cr2O7. When we say acidified, this talks about sulfuric acid. It is laced with this. So let's assume we have ethanol, and then we are adding potassium heptaozodichromate 6 to this particular solution. What will happen is that if you look at the difference between this ethanol and this ethanol, the difference there is hydrogen. 2 hydrogen has been removed here. We have 2C, CC, H5 plus the H here, that's H6, H3 plus H1, that's H4, oxygen. So the difference here is hydrogen. Where has the hydrogen gone to? The hydrogen had actually moved to the acidified potassium heptaozodichromate 6. So the hydrogen is moving here. So when you look at the fact that from ethanol to ethanol, this process here is oxidation, removal of hydrogen from a substance, and that's talking about ethanol being converted into ethanol. But then the hydrogen from the ethanol is going to acidify potassium heptazoate dichromate 6, and here the color of the potassium heptazoate dichromate 6 is actually orange, and once hydrogen is added to this, it is going to change to green. In this situation, what we usually undergo oxidation is the reducing agent. So the ethanol here is the reducing agent. It had undergone oxidation so that it is converted to ethanol. Now, hydrogen has been added to K2Cr2O7, that's potassium heptazoate dichromate 6. Addition of hydrogen to a substance is reduction, so that K2Cr2O7 here that had undergone reduction is the oxidizing agent, In one of the tests for reducing agent, we use in the test for reducing agent, we use potassium heptazoate dichromate 6, because when we add potassium heptazoate dichromate 6, K2Cr2O7, to any solution or to any substance, once the color changes from orange to green, plus let's say a substance S, once we add this to this, it means that this substance, hydrogen has been added to this. That's what it means. And in that regard, it means the substance here is just like what we've done here. The substance is a reducing agent. So in the test for reducing agents, once we add acidified potassium heptazoate dichromate 6, the color is expected to change from orange to green. That's one of the tests for reducing agents. Even in this case, if we use KMNO4, talking about potassium tetraoxomanganate 7, the color is going to change here. The color of KMNO4 here is purple, some say pink. This will change to colorless. So if I add this to any solution and the color changes to colorless, the pink color or the purple color changes to colorless, it means the substance I have added this to, it means the substance is a reducing agent. So in the test for reducing agents, we can use K2Cr2O7 or KMNO4. The color change there tells us that the substance to which we are adding K2Cr2O7 and KMNO4, it means those substances are reducing agent. But don't forget, we're looking at redox reaction in terms of hydrogen, talking about ethanol to ethanol. Hydrogen has been removed there. Removal of hydrogen from a substance is oxidation. See, removal of hydrogen from a substance is oxidation. What we undergo oxidation is the reducing agent. Now, where has the hydrogen here gone? The hydrogen has been added to K2Cr2O7. Addition of hydrogen to a substance is reduction. So what we undergo reduction, oxidizing agent. Take note of the color changes, and this here are some of the tests we use in identifying reducing agents. Once you add them to any reducing agent, if there is a substance, once you add them to any substance, if the color changes, then it means those substances are reducing agents. Now, moving on, let's look at redox reaction in terms of electron transfer. Now, talking about redox reaction in terms of electron transfer, oxidation is loss of electron and reduction is gain of electron. We can use this acronym OIL-RE. Oxidation is loss of electron from a substance. Now, talking about the elements we have in the periodic table, what are the substances that usually lose electron? There are substances with 1, 2, or 3 valency electrons. Substances with 1, 2, or 3 valency electrons, they are capable of losing electrons, and they are our metals. They are the metals. And what usually undergo oxidation, we talk about reducing agents. So invariably what this means is that metals are reducing agent, where reduction is gain of electron. Let me write that out. Oxidation is loss of electron, oil, then reduction is gain of electron, oil re. So what are those elements that gain electron according to the periodic table? You're talking about elements with 5, 6, or 7 electrons. So they are going to accept 3, 2, and 1 electron to attain octet electronic configuration. So those are the non-metals. And what usually undergo reduction, talking about reductions, are the oxidizing agents. So non-metals are oxidizing agents, whereas metals are reducing agents. Don't forget, oxidation is loss of electron from a substance, while reduction is gain of electron to a substance. Reduction is gain of electron to a substance. So let's use equations to further understand this. Let's take a reaction between, let's look at the reaction between magnesium and oxygen. Okay, magnesium is the 12th element, so that's 2 in the first shell, 8 electron in the second shell, and 2 8 2, number 12. And then oxygen is number 8, 2 6, because it exists as a molecule, 2 6. So for magnesium to attain octet configuration, it gives out these 2 electrons. So there are 2 electrons to oxygen here. The oxygen here will attain octet configuration. So you're looking at MgO, magnesium oxide. So ionically written as Mg2 plus O2 minus. So when you look at this is loss of electrons. So in order to have a balanced equation here, we need another magnesium, so that 2 electron goes here as well, so that we have another magnesium, so that this is 2 MgO. That's 2 Mg 2 plus O2 minus. So when you look at this, oxidation is loss of electrons. So magnesium to become this, that tells you that is oxidation. The one that loses electron is the metal. You see, is having 2 electrons in the valency shell. Oxidation is loss of electron. What undergoes oxidation is the reducing agent. So here we say magnesium here is the reducing agent. So when we talk about oxygen here had gained 2 electrons to attain octet configuration. So the process of gaining electron is called reduction. And what we usually undergo reduction is the oxidizing agent. Are pretty direct. In fact, we can take as much example as we can take. If you look at it, let's say we have a reaction between sodium and chlorine gas, for example. When you look at sodium is 281 as the 11th element, and chlorine is 287. But because chlorine exists as a molecule, so you're looking at 287. For chlorine to attain octet configuration, it needs 1 electron. For sodium to attain octet, it needs give out 1 electron. Okay, let's give 1 electron here, so that once this happens, what we have is Na plus, it has lost 1 electron, and then chlorine had gained here Cl minus. So this is NaCl. But because we have another chlorine here, you're going to be looking at 281. We need another sodium, so that it gives 1 electron to this. So what are we going to have here is another Na plus Cl minus. So that is 2NaCl. When you look at sodium here, the fact that sodium had lost electron, this is oxidation. And what we undergo oxidation is the reducing agent. Now talking about chlorine, gain of electron in this case. Gain of electron is what we call reduction, and what we usually undergo reduction is the oxidizing agent. So this is just how this works, and there is no dilly-dallying about this. In fact, when you look at this, look at the oxidation state of magnesium here, it is 0, and now the oxidation state has become +2. Look at the oxidation state of oxygen here, and the oxidation state has become -2. Look at the oxidation state of sodium. When an atom is standing alone, the oxidation state is 0. So sodium here is 0, chlorine here is 0. They are in the uncombined state. But look at what had happened. Sodium has become +1. Chlorine has become -1. That's going to take us, this is in terms of electron transfer, that is going to take us into what we call oxidation number concepts. Oxidation number concepts. For oxidation number concept, that's trying to look at redox in terms of oxidation number, you need to understand that oxidation is an increase in oxidation number. You look at it, magnesium had increased from 0 to +2. Sodium had increased from 0 to +1. Oxidation is increase in oxidation number, while reduction is a decrease in oxidation number. So what I'm saying here is that in as much as oxidation is loss of electron and reduction is gain of electron, we can also look at redox reaction in terms of what the oxidation number concept. Oxidation is going to lead to an increase in oxidation number. Reduction is going to lead to a corresponding decrease in oxidation number. Take note of that now. Also, another thing you need to take note of is when dealing redox, especially in terms of electron transfer and oxidation number concept, you talk of oxidation first before you talk about reduction, because it is the electron that is lost that can now be gained. You cannot gain what has not been lost. So it is going to be a misnomer for you to talk about gain of electron when you don't even know how many electron has been lost. So we talk of oxidation first before we talk about reduction. So in terms of oxidation number concept, oxidation is what? Increase in oxidation number. So if we say oxidation is increase in oxidation number, looking at sodium had become +1 from 0 to +1. That means reducing agents will have their oxidation number increased. More so, reducing agents will usually undergo oxidation. So for a reducing agent, the oxidation number is going to increase. But when you look at something like chlorine, from 0 to -1, you have the oxidation number decreasing. That is reduction. So what will undergo reduction? Oxidizing agent. So for oxidizing agent, the oxidation number is usually decreased. So the next thing we're going to look at now is the rules we use in assigning oxidation number, and then we're going to have some calculation that has to do with oxidation numbers, as these are common questions in the JAMB UTME. Next up is the rules for assigning oxidation number. Oxidation number of elements in free or uncombined state is 0. What this means is that when you see an atom standing alone and has not combined with another atom, it means that the oxidation number or the oxidation state of that element or that atom or that molecule at that point in time is 0. Like, let's say sodium standing alone in an equation, or magnesium standing alone in a chemical equation, you assume that the oxidation number is 0 at that point in time. If I'm having chlorine, if I'm having oxygen, and they've not combined with any other element, at that point the oxidation number is 0. Also, for a compound, let's say we have HCl. In this case, the oxidation number is going to be the sum total of the oxidation number of the respective element that makes up the compound, and everything is going to be equal to 0. If I say sodium chloride now, it's going to be equal to 0. If I say magnesium sulfate, it's going to be equal to 0. So for a compound, everything equals to 0. Take note, when you talk about hydrogen, Oxidation number of hydrogen is -1, but in hydride it is -1. I need to emphasize more on this. Now, usually when we have a compound, like let's say the way we have sodium chloride here, sodium chloride. Sodium here is a metal. Chlorine here is a non-metal. So the metal is expected to lose electron. That's oxidation. Whereas the non-metal, chlorine here, is expected to accept or gain the electron. That is the non-metal. You have sodium chloride, not chloride sodium. That's not possible. You don't gain electron first before loss of electron occur. So the metal has to lose the electron, and then the non-metal will gain the electron. So what does that have to do with the case of hydrogen? If I have HCl here, hydrogen is coming first, taking the place as though it is a metal. Although we know hydrogen is not a metal, but in this case, the fact that hydrogen comes first means hydrogen is more or less performing the role of a metal, whereas chlorine is here acting as a non-metal. In this case, then your hydrogen is +1. But in a case where hydrogen is taking the place of a non-metal, as you can see in this hydride, sodium hydride, when hydrogen comes last, what usually comes last in a compound, if it's not the radical, what usually comes last is usually the non-metal. So in this case, hydrogen is performing the role of a non-metal. So in that case, that's what I mean by saying in hydride, then hydrogen is -1. So it's just a case of knowing when to use +1 and knowing when to use -1. When hydrogen comes first, let's say like in HCl, like in H2SO4, you give hydrogen a +1 oxidation number. But when hydrogen takes the role of a non-metal, coming last in a compound, then you assign -1 to hydrogen. So that's the first two rules. When in the uncombined state, elements or molecules are given oxidation number of 0. For a compound, the sum total of all the oxidation number equal to 0. In the case of hydrogen, if it comes first and takes the place of a metal, hydrogen is assigned +1. But when hydrogen comes last, taking the place of a non-metal, hydrogen is assigned an oxidation number of -1. Still on rules for assigning oxidation numbers, when you have an ion, the charge on the ion is simply the oxidation number. Like in the case of aluminum, if you once you know your first 20 elements and you can think in terms of duplet or octet electronic configuration, most atoms try to imitate the octet or duplet electronic configuration of the noble gases in group 8 or group O closest to it. Like in the case of aluminum is element number 13. That's 283. So it has to give out 3 elements with a valency electron of 1, 2, or 3. Give out those electrons to attain stability. So in the case of aluminum ion, now the 3+ here is the oxidation state. In the case of ion, it is Fe2+. Okay, let's say calcium, for example. Calcium is element number 20. So if you look at the distribution, that's going to be 2, 8, 8, 2. So you expect calcium to give out these 2 electrons to attain octet electronic configuration. What that means is that the oxidation state of calcium is going to be Ca2+, because it has given out 2 electrons to attain octet configuration. So oxidation number of an ion is the charge on that ion. Then talking about radicals, radicals are a group of atoms acting as a single unit. This is triosocarbonate 4 ion. So the oxidation number here is of HCO3 here is the charge you have there. So what this means is that HCO3 equals to -1. And what this means here, triosocarbonate 4 ion, it means that CO3 equals to -2, and this means this equals to -2. Hydroxyl here equals to -1. So those are just about the important rules that we need talking about oxidation numbers, also taking note at least at this level of your first 20 elements and thinking in terms of stable octet or duplet electronic configuration. That way you'll be able to flow. So let's quickly get into it. Let's calculate oxidation numbers of elements. Okay, I haven't talked about the rules for assigning oxidation number. Let's quickly look at calculation of oxidation numbers. Take for example, this is a UTME question. It says calculate the oxidation number of chromium in K2Cr2O7 read as potassium heptaoxodichromate 6. Let's assume I don't even know what chromium represent, because chromium is not in the first 20 elements, which of course most science students at this level, we just limit ourselves to the first 20 elements. So how do you go about this? Very simple. In this case, you want to know the oxidation number of chromium. You're talking about chromium. That is the question here. Now when you look at this, potassium is element number 19. When you look at the distribution of electron, you talk 2, 8, 8, 1. That's number 19. For potassium to attain octet configuration, it needs to give out this. And when potassium give out that one, that's K plus. So in this case, potassium is +1, but I have a subscript of 2 here. So that is +1 times 2 for potassium. For my chromium, I'm going to say let my chromium represent X. So X times 2, that is going to be +2X. Now talking about oxygen, oxygen is element number 8. If you look at the distribution of electron, talking about the atomic structure, you're looking at 2 in the first shell, 6 in the next shell. And when you look at this, for oxygen to attain octet configuration, it needs 2 electron. It needs 2 electron. So when it accepts 2 electron, oxygen is going to become O2 minus. So the oxidation state of oxygen here is -2. So you're looking at -2 times 7. So according to the rules for assigning oxidation number for a compound, everything, the whole of the summation of all the oxidation number equals to 0. So when you look at this, +1 times 2 is 2, +2x minus 14 equals to 0. 2 is going to move here, so I'm going to have 2x equals to -2 plus 14. So 2x equals to 12. So x equals to 12 over 2. So x equals to 6. That means oxidation state of chromium equals to +6. So that is how it works. Take for example, if I tell you in KMNO4, I want you to get the oxidation state of manganese. Potassium is +1. Plus, let manganese be X. Oxygen is -2. That's going to be -2 times 4 equals to 0. So in this case, this is going to be +1 plus x minus 8 equals to 0. So x equals to 0 plus 8 minus 1, x equals to 7. So you're looking at manganese here equals to 7. That is why we read this as potassium tetraoxomanganate 7, read as potassium tetraoxo. This manganate now, because of the oxidation number +7, that is why we talk potassium tetraoxomanganate 7. And here, potassium heptaoxodichromate 6, read as potassium heptaoxodichromate 6. So it is based on the oxidation number, and these two questions here are UTME question. Let's take another question. Let's assume we have H2SO4 and we're told to look for the oxidation state of sulfur here. Of course, hydrogen, I told you once it starts a compound, hydrogen is assigned +1. So this is going to be +1 times 2. plus, I'm looking for sulfur, let sulfur be X, plus oxygen is minus 2 times 4. For a compound, everything equals to 0. So what we have here is going to be 2 plus X minus 8 equals to 0. Therefore, X will be 8 minus 2, X equals to 6, plus 6 in this case. That is why when we read this is going to be hydrogen tetraoxo sulfate 6. Hydrogen tetraoxo sulfate 6. Okay, let's take another question. This is also a UTME question. Imagine we have sodium, the B here represents boron, and then hydrogen here is 4. In this case, here hydrogen starts this compound, so it's assigned +1. But here hydrogen is taking the role of a is performing the role of a non-metal, is in the space of a non-metal. So sodium is 11th element, so that is 2H1. Sodium is going to be +1, plus, if I'm looking for the oxidation state or the oxidation number of boron, okay, let boron be X here. Hydrogen here is going to be given -1 times 4, all equals to 0. So this is 1 plus X minus 4 equals to 0. So this is going to be X equals to 4 minus 1, X equals to 3. So moving on, the next thing is what we call half equations. When we say half equations, it simply means you want to separate a given redox reaction into oxidation separate and reduction reaction separate. So what that means is we want to use half reactions to better understand oxidation reduction reactions. Let me use this analogy first. If I have X plus Y such that X is giving me X plus and plus Y minus. Well, what this means, recall that we've said oxidation, in terms of electron transfer, oxidation is loss of electron, whereas reduction is gain of electrons. And here we've said that for oxidation is loss of electron. What we lose electron, we talk about our metals, and what we lose electron, loss of electron is oxidation. What we undergo oxidation here is reducing agent. And at the same time, we've said reduction is gain of electron. What we gain electron, we're talking about the non-metals. And what we undergo reduction is the oxidizing agent. Also, we've said oxidation is increase in oxidation number, and whereas we've said reduction is decrease in oxidation number. So looking at this, if I have X here, the oxidation number here is 0, and if that 0 had become +1, increase in oxidation number is oxidation. So when we're talking half equations, it simply means separate this into oxidation and separate also into reduction half reaction. In the case of this, for X to become X plus, what that means is X to become X plus. It means that X had lost 1 electron. Loss of electron is oxidation. When you are losing electron during oxidation, you lose the electron on the product side of the reaction plus electron. This reaction here is talking about oxidation half reaction. And what we undergo oxidation is the reducing agent. Now, talking about Y. Y in this case had become Y minus. It means that gain electron, that is why it's becoming negatively charged. More so, reduction is decrease in oxidation number. So once we're talking reduction here, reduction is gain of electron. You gain the electron loss during oxidation, so that is plus 1 electron. And talking about gaining electron, you gain the electron on the reactant side. This here is reduction. And what you have here is that what you undergo reduction is the oxidizing agent. So this is separating this reaction here into oxidation half reaction and reduction half reaction. Now, looking at a certain reaction we used under oxidation in terms of electron transfer, let's say magnesium plus oxygen, okay? Magnesium is 2H2, oxygen is 2,6. A single magnesium takes care of one oxygen, but in this case, 2 minus or 2 plus for magnesium, 2 minus for oxygen. So I'm going to need 2 magnesium to balance the 2 moles of oxygen here. So this is basically what we have. If I'm to separate this into half reactions, what this will mean is 2 mg. So that will give me, for each magnesium, each of the magnesium will lose 2 electrons. So you're looking at 2 mg plus 4 electron. So in the case of oxygen, this is O2. For this oxygen, if this 4 electron is this here is oxidation half reaction. O2, if this accepts the 4 electron, is going to become 2O2 minus. This is the reduction half reaction. So what this basically means is that my magnesium here is the reducing agent because it is the one undergoing oxidation, whereas my oxygen here is the oxidizing agent. It is the one undergoing reduction. So what we're saying is that when we have redox reactions and we are looking at things in terms of electron transfer, we usually can separate the reactions into half reactions. You deal with your oxidation first and you deal with your reduction next. Also, before a reaction qualifies as a redox reaction, there must be a change in the oxidation number. This here is very important because there are UTME questions where we will be asked to determine which of the following set of reaction is a redox reaction. For a reaction to qualify as a redox reaction, there must be a change in oxidation number. Look at this here. This is 0, it is now +2. This here is 0, it is now -2. So in any reaction where there is a change in oxidation number, then such reaction qualifies as a redox reactions. Okay, let's take more example. Let's look at this reaction between talking about half equations. Let's look at, okay, zinc dipped into a solution of copper sulfate solution. Okay, copper sulfate is actually a blue colored solution. Once you dip zinc into this, what will happen is normally you're going to have zinc sulfate with reddish brown deposit of copper. Now, in writing this in form of half equations, in identifying what is the reducing agent, what is the oxidizing agent, the best thing is to write this ironically. In the uncombined state, zinc here is not charged, it's more or less 0, okay, plus copper here is combined with SO4. So when you talk about SO4, SO4 is SO4 2 minus. For copper to be beside SO4 2 minus, it means my copper is Cu 2 plus and then SO4 2 minus. And then looking at my product, zinc here is standing beside SO4 2 minus, so that must be Zn2 plus. And then here I have SO4 2 minus, and then copper is standing alone here. That means copper, is having oxidation state of 0. So you see, anything that is the same on the product side with the reactant side, strike them out. So in this case, zinc here is having oxidation state of 0. It's not the same thing as 2 plus. Cu2 plus here is having oxidation state of +2. On the product side, it is 0. So when you look at this, SO4 2 minus and SO4 2 minus appears to be what is the same on both sides. So when you look at zinc is not charged here. So from 0 to +2, that's an increase in oxidation number. So in fact, I could write this out as this for Zn plus Cu 2 plus to give me Zn 2 plus Cu. So when I look at this and I'm told to identify the oxidizing agent and the reducing agent is very simple. This is 0 to +2. Increase in oxidation number is oxidation. So zinc here is going to be my reducing agent. But when you look at it, copper is +2 to 0. That's a decrease in oxidation number. A decrease in oxidation number is reduction. So what we undergo reduction here is going to be my oxidizing agent. If I'm told to write this in terms of half equations, I have to always talk about my oxidation first. This is my oxidation process. This is my reduction process. So this is going to mean zinc to become Zn2+. It means here it has not given out electron, but now it has given out electron. For oxidation, you give out the electron on the product side. This is the oxidation half reaction, and that means that my zinc here is the reducing agent because it is the one undergoing oxidation. Then you talk about copper 2 ion, Cu2+. It is going to gain that 2 electron to become deposited as copper. So you gain the electron for reduction half reaction on the reactant side. So in this case, if I am asked what is my reducing agent, this is reduction, of course, this is looking as though it is my oxidizing agent, because oxidizing agent is meant to undergo reduction. But if I am being asked, copper 2 ion Cu2+ is not my oxidizing agent, but rather my oxidizing agent is, I go back to the start of the equation, this is going to be my oxidizing agent, copper sulfate, because the copper 2 ion is actually inside of the copper sulfate. So what am I trying to say is, when you talk about redox reaction, to understand it better, we can also use half equations. Okay, moving on to ensure that this concept of half equations and using that to understand redox distills quite well. Let's look at this equation. As you can see on your screen, we were told to write the oxidation and reduction half reactions for these net redox equations and show that their sum is the net reaction. We have this cadmium plus copper 2 ion to give us copper deposit and cadmium 2 ion. In this case, what you have to look out for, I've always said you look out for your oxidation first, and you know oxidation is increase in oxidation number. When you look at cadmium is having oxidation state of 0 and it had increased to +2. So if I'm writing this, this is going to be cadmium to give me cadmium ion. For oxidation half reactions, I lose the electron on the product side. So what I have here is +2 electron. Talking about copper 2 ion, 2 + to 0, that is a decrease in oxidation number. Reduction is a decrease in oxidation number. And what you undergo oxidation is your reducing agent. What you undergo reduction is your oxidizing agent. So looking at what we have here, this is oxidation for cadmium, because the oxidation number had increased from 0 to +2. Talking about copper, this is Cu2+. The electron being lost at the oxidation stage will be gained at the reduction stage. And what you're going to have here, you gain electron on the reactant side for reduction. What you're going to have is copper deposit. This is reduction. Overall, if we are to write the overall equation for this, this is cadmium plus copper. Ignore the electrons here. This will give us cadmium 2 ion plus copper deposits. So this is the overall equation. This is what we have here, and that's exactly what we've started with. So if I'm being asked what is the reducing agent here, my reducing agent is the one that undergoes oxidation. Cadmium is my reducing agent, and my oxidizing agent is the one that undergoes reduction. Copper 2 ion is my oxidizing agent. Pretty direct. Looking at the second question, as you can see on your screen, is the reaction between zinc and hydrogen ion to give us zinc 2 ion plus hydrogen gas. In this situation, just as we've done for the first one here, what we'll be doing here is zinc, okay, to become, this is 0 to plus 2, that is oxidation, increase in oxidation number, Zn2 plus, that's plus 2 electron, and so this is oxidation. But when you look at hydrogen ion, plus 1 to 0, this is plus 1 to 0, that is a decrease in oxidation number. So 2H plus the 2 electron, lost during the oxidation half reaction, this is going to become hydrogen gas. So if I'm being asked what is my oxidizing agent here, what is my reducing agent, my reducing agent is the one that undergoes oxidation. So in this case, that is my zinc methyl, and my oxidizing agent is the one that undergoes reduction, that is my hydrogen ion. So this is direct. Now moving on to question 3, as you can see, the process always consistent. When you look at aluminum here, aluminum is 0, it has increased to plus 3. So if I'm to write the half equation here, this is 2Al, okay, this is giving me 2Al3 plus. You lose the electron on the product side. Increase in oxidation number, this is 0 to plus 3. And in this case, because I have 2 aluminum, this is going to be 6 electrons. Each aluminum is losing 3 electrons. That's what this means, Al3 plus, but I have twice two moles of aluminum, so that's 6 electrons in this case. So that is my oxidation half reaction. For my reduction half reaction, I have 3 moles of zinc 2 ion, accepting that 6 electron, and I'm going to have 3 moles of zinc deposited. A decrease in oxidation number from plus 2 to 0, that is reduction. So that if I'm asked what is the reducing agent, what is the oxidizing agent, reducing agent undergoes oxidation while oxidizing agent undergoes reduction. And with that, we've come to the end of our half equations. How do we determine if a reaction is redox or a reaction is not redox? If a reaction is redox, then there must be a change in the oxidation number. If there is no change in the oxidation number, then that reaction is purely not a redox reaction. And let's take this example to determine if this is redox or not. Let's look at the reaction between lead triazonitrate 5 and sodium chloride. And in here, I'm going to be having, lead 2 chloride plus 2 moles of sodium triazonitrate 5. So if I'm told to determine if this is redox or not redox, what am I going to do? I'm going to express this in the ionic form. So triazonitrate 5 here is actually NO3 minus. For me to have 2 of this, that means my lead is actually Pb2 plus sodium is 2Na plus, chlorine is 2Cl minus. What I have here is lead with chlorine here, this is Pb2 plus 2Cl minus plus 2Na plus then 2 NO3 minus. Whatever is the same on the reactant side and on the product side, you get that out. This is Pb2 plus, I have Pb2 plus, no change in the oxidation number, this out. This is 2 moles of charcoal 5. On the product side, I also have 2 moles of charcoal 5. This is 2 moles of sodium. Here, I also have 2 moles of sodium. This is 2 moles of chlorine. I also have 2 moles of chlorine. So you see, at the end, I'm left with nothing. That tells me that this is not redox. Because if it were to be redox, there will be changes in the oxidation number. So here, no change in the oxidation number. Let's look at another one. Let's say a reaction between H2SO4 plus sodium hydroxide. In this case, what I'm going to have is Na2SO4. Okay, I'm going to put 2 here plus 2H2O. Okay, if I'm to determine if this is a redox reaction, I have to express it in form of ions. This is 2H plus SO4 2 minus plus 2Na plus 2OH minus. This is going to give me 2Na plus SO4 2 minus plus. Water means H plus and then OH minus, but because I have to, that's 2H plus and 2OH minus. 2H plus strikes out 2H plus. SO4 2 minus takes out SO4 2 minus. 2 moles of sodium takes out 2 moles of sodium. 2 moles of hydroxyl takes out 2 moles of hydroxyl. So no change in the oxidation number. So as I'm not seeing any change in the oxidation number, even when I've expressed it in form of ions, that tells me this is not a redox reaction. In fact, this is more specifically a neutralization reaction. The first one I have here, when you look at it, lead takes the place of sodium here. Sodium takes the place of sodium. This is more like a double dissociation or double displacement reaction. But imagine I have a reaction like this. Let me have a reaction like this, where I say, okay, FeCl2 plus chlorine. When iron 2 chloride reacts with chlorine gas, this is what I'm going to have, FeCl3. So having FeCl3, this is 2 here. If I try to put 2 here, so this is what I'm going to have. Okay, if I put 2 here. Now, this is a balanced equation. Now, merely looking at this, I am going to, if I'm told to determine if this is redox or not, I'm going to conclude that this is redox because I've been able to spot something very direct here. And what I have spotted is this. Oxidation state of chlorine here is 0. But that chlorine now had combined with iron, and I cannot see any chlorine having oxidation state of 0 in this case. Looking at this, for iron to combine with 2 moles of chlorine, that means you're looking at iron 2 ion. But I have 2 of this, 2 times 2. This is 4Cl minus plus Cl2. So for iron to combine with chlorine, that means this is Fe3 plus. And then this should have been 3Cl minus, but having 2 here, 2 times 3, that's 6Cl minus. Firstly, this is 2 plus, this is 3 plus here. That tells me there is a change in oxidation number. When you look at it, okay, I said whatever is the same on the reactant side and on the product side, strike them out. This strikes out this. So I'm going to be left with 2Fe2 plus Cl2, so that I'm going to have Fe 2Fe 3 plus. So since 4Cl minus had cancelled 6Cl minus, I'm going to be left with 2Cl minus. So it simply means oxidation state of chlorine is 0 and it had now become minus 1. So there is a change in oxidation number. So it's very easy to tell that this is a redox reaction. In fact, you only just need to look at it. This is 0 and this has now added to this. There must be a change in the oxidation number. It's no longer standing alone. So when you talk about reactions, how you identify if a reaction is redox or not redox is if there is a change in oxidation number. And with that, we've come to the end of redox reaction, being the first topic under the theme electrochemistry. So next up is going to be purely UTME questions that has to do with oxidation reduction reaction, so that you can see what question looks like in the exam, and that way we begin to take quality steps forward in making sure that the team electrochemistry we get our 15 marks in the bag. So for myself and the entire team, it's bye for now.